Okay, then we continue. Now we do what we have said. We neglect, instead of neglecting these terms, we consider them. Underline red in equations 7a and b. So instead of neglecting these, and the people who did that first to this new approach, that were Dormel and Wraithby. They approximate them. And they approximate the values of u at the neighboring nodes, that is the velocity perturbation in x direction, that is approximated by the value at the center node, which is uij prime. And correspondingly, the velocity correction in the y direction, v and v prime, is approximated by the v at the center node, which is in that case capital I lowercase j prime. If we do that, we get, so from that, we obtain then equation 8, that is then that the uij prime is now similar as for the simple, but now the coefficient d that we get here with the simplex will be different. We have still the pressure corrections of the neighbors, Pij minus I minus 1j, so this is the prime, the pressure corrections. And the difference is now that the d coefficient here is then the following. Dij is the area that we have at that face, ij divided. Now we have the center coefficient, and if we do it in this way, we get also the neighboring coefficients there. So we get minus the sum over the neighboring coefficients. In the simple, we just had this. So this is now the change, that the d coefficients are changed by this term. But there is a thing that one should remember, that the center coefficient, ui capital J, minus the sum over the neighboring coefficients, as we said when we wrote down this center coefficient, that is the mass flow over the control volume. And that we can write as the mass flow over the eastern minus the western, plus the mass flow over the northern minus the southern phase. So that is the net mass flow over the boundary of the control volume. And that can be considered as the continuity error. So an error in the continuity equation. So if that has some value, then the mass flow, the net mass flow that should be zero for incompressible flow is not zero. But in the process of the iterative process, we usually have this non-zero. If this quantity here, that is the net mass flow of the boundary control volume, is zero, then we are finished, because then our velocities are such that they fulfill the continuity equation, the corresponding pressure is such that it supports that. So then we can stop. do not need to correct velocity of pressure. And then we could, if we have this, if we want to just to have the algorithm then working, we could simply say then that we say the dij we could put it to 0 in that case. So the problem that you can observe, if this mass flow rate is 0, then the denominator is 0. So that is the case that we discuss here. So then, but when it is 0, then the mass flow error is 0, and then we have reached a velocity, the corresponding pressure, that satisfy the continuity equation. So a similar, what we said here for the x momentum equation, the coupling between the u and the pressure perturbation, so the velocity perturbation in x, and the pressure on the neighbors, we can say also about the coupling for the velocity perturbation in the y direction. So that means we get a similar argument. Similarly, we get, that is 9, that the velocity perturbation in the y direction, Tij prime, is equal to minus Dij times, now we have the pressure perturbations at the corresponding northern and southern neighbors for this, and that is the P prime Ij minus 1. And the D coefficient here is then the Dij, that is the area of the corresponding face, divided by the center coefficient now for the y momentum equation, Ai minus the neighbors, the sum of the neighboring coefficients. And here the same remark applies as we had here. Remark on denominator. As for equation 8. So then we have the relations 8 and 9 that couple then velocity and pressure, and that gives then a consistent coupling, and therefore we have the name simplex, simple consistent. Pressure velocity couplings that are used in the method that we have just discussed. Simplex, that stands for simple consistent. As now opposed to simple 8 and 9, these velocity pressure couplings that we derived are consistent. No under-relaxation of P is needed. No under-relaxation of P. And that means the following, that we can evaluate the pressure by the preliminary pressure, which is then the current one that we have. In the beginning it is the guessed pressure, and when we are in the iteration process it is the latest value of the pressure. And then we simply add the P prime directly. And that means if you compare that with a simple, in the simple we had here an alpha P. And this alpha P here then means that here it is 1. So we don't have it. We don't need it. So then we have this method, which is very similar to the simple method. The only difference is that the coefficients for the coupling are a little different, taking the neighboring coefficient into account. So if we now look at the flowchart for the simple algorithm, that flowchart will also apply for the simplex. So if we start from the top, we guess the P star, U star, V star, phi star. Imagine temperature in our case would be an example. Turbulent kinetic energy, dissipation rate if we have a turbulence model, K epsilon. Then we solve the discretized momentum equations. There we go. So we solve the discretized momentum equations, get the U star and the V star, and then we solve the pressure correction equation. And then we get the P star, and then in the pressure correction equation, let's see, it is now coming here. So the change D is coming here. When we enter, let's see. When we have solved the pressure correction equation, then we correct the pressure, and without under relaxation, here it is correct. For the simple, we would have here an alpha P sitting here. An under relaxation, smaller than 1. And the rest is then the D coefficients, and they would then be the ones that we have here for the simplex. Otherwise, we would have the ones for the simple, which are the same as these, without these terms. So then we correct the velocities, U and V, and then we solve the additional transport equations, for example, the energy equation, K epsilon equation, and so on. And then we check the convergence. And if we have convergence, then we are finished. We stop the program. Otherwise, we go to the next iteration by taking the pressure, the preliminary pressure, P star as the current one, the velocity components as the current ones, and the phi star as the current one. And then we go through the loop until we have convergence. So that is the process of the simple and the simplex algorithms. We have still another option that we want to discuss, that is the simpler algorithm, which does it a little bit differently than the simplex. But they are all based, all these methods, on the simple algorithm itself. So then first the name, simpler. So the R, that will stand for simple revisited. So the application of the simple approximation has shown that it leads to an efficient velocity correction but to a poor pressure correction. And therefore Patanka proposed simple revisited. That is actually Patanka and Spaulding, one of the authors of Simple itself, also author of the book on where these basic methods are explained. So he proposed simpler, which stands for simple revisited. The idea is the following. We determine the pressure now not by a pressure correction equation, but by a consistent Poisson-like equation. So Poisson-like, so it's like a Poisson equation. And the important thing is that we compute the pressure directly, not the pressure correction. However, we still use the pressure correction equation as for the simple algorithm, but we use it only to correct the velocity, not the pressure. So the pressure is determined by a consistent equation directly. So now we look again at the form that we are solving of the equations, and we look first at the discretized x-momentum equation. So the discretized x-momentum equation can be expressed as the following. That is following. So the u lowercase I capital case j, remember we are always discussing here this in unstaggered grid, is equal to, we divide by the coefficient that is sitting here, the aij. So then we get here the sum over the neighboring coefficients, where we have the neighbors of the neighboring coefficients times the velocity. So we look at the discretization of the x-momentum equation itself, so in the ideal case. Then we have here the B that is coming from a volume force. For example, if we have gravity included, that would then be in the B. And we have divided here by the center coefficient aij. And then we have here now if we write it in this form, where we have already divided by the center coefficient, we get here the d coefficient that we get for the simple algorithm. So we get here the d coefficient for the simple algorithm, that is the d capital lowercase I capital J times the pressure difference in the I direction between ij and pi minus 1j. So then we have this form, and the coefficients are the same as before, as we discussed for the simple algorithm. Coefficients are same as for simple. And now we define so-called pseudo velocity. define, and that is called U hat. U hat at lowercase I, capital J. So these guys here, they are defined now as all this here. That is defined as U hat. U hat. U hat. U hat ij. So then we have that as the sum over the neighbors, where we have the neighboring coefficients A and B, and our velocity components there in the x direction, plus the contribution coming from the volume force divided by Aij, capital J here. And the velocity components appearing, anything is appearing here is at the latest iteration. So the U and B is at latest iteration. So then we can express this equation 10 with these pseudo velocity. And if we take the latest velocity component, we compute these pseudo velocity, we can compute them. So they are then null. So then, that is equation 10, then becomes 12. That the velocity component Uij is the pseudo velocity U hat at Ij minus the d coefficient times the pressure difference between that is the eastern phase for the control volume for U, and that is now at the western phase. So then we get this expression for the relation between velocity and the pseudo velocity that we can compute. And we get similar expressions, we can derive similar expressions than in the y direction. So similarly, we define correspondingly, and we obtain them for the discretized y momentum equation. Following that we get that the velocity component in the y direction v at ij, capital I lowercase j, which is sitting at another scale place, as we know from the staggered grid. And there we get also a pseudo velocity v hat and minus the corresponding d coefficient that we have in the simple times the pressure difference. This is then for this control volume for B. This is at the northern phase, and the Pij minus 1 is at the southern phase. Now the pseudo velocity here is then defined as v hat ij is equal to the sum over the neighbors, the neighboring coefficients, the v component at the neighboring coefficients, plus now the source term in the y momentum equation, divided by the center coefficient Aij. So that is then a pseudo velocity in the y direction. Here we have it in the x direction, here it's in the y direction, so that is the pseudo velocity in y direction. And the A and the V and B are again at the latest iteration. So V and B at the latest iteration. then we can compute them. And then we have them available, and then we have this relation here. This for the relation between the velocity component in the y direction, the pressure, and here between the velocity components in the x direction and the corresponding pressure, neighboring pressure. And then we insert these relations, 12 and 13, into the continuity equation, and to get then a Poisson-like equation for the pressure itself. So when we insert the relations 12 and 13 with the pseudo velocity components into the continuity equation, we obtain the pressure-like equation for the pressure itself, the Poisson-like equation. So we obtain the Poisson-like equation for the pressure. No, it is for the pressure, not for the pressure correction. That is the difference between this and the simple. So we get then the A coefficients times the pressure at the center node. So that is now the center node for the pressure. Remember, we are always discussing here this for staggered grid what we do. The sum over the neighboring coefficients times the pressure at the neighboring coefficients plus some source term, which is Eij. So when we do the derivation, we find out that the A coefficients so both for the center, for the neighbors, and for the center one are exactly the same as for the pressure correction equation. That we use for the simple method. But the difference is the B. The B, that is the source term here, is then defined in terms of the pseudo velocities. So that is the rho A u hat, and that is at I plus 1j when we do it, and here we can rho A u hat times the ij, and then we have a contribution from, that is now the east and west. Now we have contribution from the north, from the mass flow there, rho A v hat, that is at I j plus 1 minus rho A density area pseudo velocity in y direction at ij. So that is, so it's minus the mass balance for the pseudo velocities. So that means that it's similar to the B in the pressure correction equation, but it is not based on the preliminary ones, velocity components U star and V star, but on the pseudo velocities. So that is the difference. So that means that we have here the B, Ij is similar to corresponding a value in the pressure correction equation. But it is defined here in terms of the pseudo velocities, u hat and v hat, instead of the preliminary ones, u star and v star. So that is the difference. And as the equation 14 is consistent, again, no unrealization is needed. Here for the simpler method, this pressure equation 14 is consistent no underrealization is needed. So when we have computed that, the P here, that is then the first thing that we do then we call that the P star. So the computed P from 14 is then used as the P star in the momentum equations. So that we do then in the beginning, and then we continue. So then the preliminary velocity components are then computed next, and they are determined from the momentum equations. So that is now the step afterwards. First this step, and then now we compute the preliminary velocity components that are the u star and the v star are determined from the momentum equations. So solve them first, say the x momentum, y momentum, would be 3D, but also the z momentum. Next step is then, now we are again in the simple mode, we solve the pressure correction equation. So, pressure correction equation is solved and that is so that then we get the P prime from that. So from that we get the P prime, pressure correction. But with that P prime we only correct the velocities. Yes?
What does the sign, the O, mean? Well,
It is, you can do it like that, it means the bullet point.
okay, yeah.
So, then we use only P prime to correct the velocity components. So P prime is only used to correct the velocity components. And that is then using the simple ansatz. Use correct velocities by the simple ansatz. That is important, not pressure. Pressure is not corrected because we have already good pressure by solving this consistent pressure equation. So that is then, so first step, so for the pressure. Second step, solve x and y momentum equation, get the u star p star. Third step, solve the pressure correction equation, S for simple, get the p prime, and then only correct the velocity components, not the pressure. So then we can solve additional transport equation. So additional transport equation. Are solved, for example, equation, K equation, epsilon equation, whatever you like. The energy equation as an example also. Okay. And if convergence has not yet been reached, we use the current velocity components to compute the new iteration by solving again the pressure correction. So then we go over the loop again. So although this approach is more costly, why it is more costly? We have the same work as for the simple, because here we have to solve for u star and v star. We use the implicit method, so we have to solve a system here for u star and v star. Here we have to solve a Poisson-like equation for p prime, and in addition we have to solve a Poisson equation for p itself. So that is an addition. In spite of that additional work, this converges faster than simple. So simplex and simpler have a similar performance, and so they outperform, although they need more work than the simple algorithm. Yes?
You said that you used p prime, the current velocity, but
Yes.
in question 10, 12, and 13 you only use p prime.
We are using the simple algorithm. In the simple algorithm, we use the p prime.
Not in simple.
The simpler algorithm uses simple. So it uses the pressure equation to determine the pressure, but it uses simple in the same way as simple. So therefore it is p prime. So that is the same. These parts here, also this part is the same as for simple. The difference is that with the p prime, the pressure is not corrected, but instead we take the pressure that we have determined with the pressure equation for T. That is the difference. So if we look at that in a graph, then we have the simpler here. Start from the top. So the first thing here is to get the pseudo velocities, and that is not so much work. The work is then solve the pressure equation. Of course, that is a Poisson-like equation that is costly. Then we set the p star equal to p, and then we solve the discretized momentum equations. But that is similar as we have done for the simple already. And then we do the correction, you see here, only for the velocity. U and V. With the U star and the V star. That are the preliminary velocity computed in the momentum equations. And then we solve for additional transport equations. So the more work that we do here is by solving this pressure equation. Get the pressure. But we still have the pressure, so we have to solve the pressure correction. Nevertheless, this work pays off because then we have a consistent method and we need fewer iterations to get convergence. Okay, so we stop here and you can read more about that in the textbook that is relevant for this part, that is by Versteeg and Müller. You have the old edition available.